I'd like to think that by now we have learned a thing or two in this course. So back in lecture 2, besides, learning what the word compression meant, we also learned that it's healthy to temper our expectations with compression, because no matter what clever compression scheme we design, if it ever achieves compression on any inputs, it's also going to expand some other inputs. And the reason that that's sort of liberating is that, well, if we know we're going to get some expansion one way or the other, we shouldn't be too hard on ourselves if we discover an input that expands. But on the other hand, that changes the strategy that we should focus on when we're designing our compression schemes. If we know that some inputs will compress and some inputs will expand, well, we obviously want to minimize the amount of expansion that tends to happen, but also we want to relegate the inputs that expand to be those inputs that we're unlikely to see. So we've already discussed this focus on compressing real data, the kind of data we're likely to encounter in practice. I'd like it if the schemes that I develop give me good compression on real data, or at least they don't expand it too much, whereas if I try to compress something like random noise, so a bunch of random bits I'm keeping around, and we'll talk more formally about what I mean by random noise in a couple of lectures. The idea that data that doesn't contain any internal patterns of any sort is probably difficult to compress. If I try to compress random noise, maybe that gets expanded. And I use the reasoning that it's sort of unlikely that people are going to try to compress random noise more often than real data. And also, frankly, because it's well understood by people that use compression that random noise doesn't compress very well, if somebody does have a file of random bits lying around and they try to compress it, they probably wouldn't be too upset if it turns out to expand, because they understand that the more randomized the data is, the less likely I'm going to be able to get good compression out of it. So those are a couple of things we understood from lecture number 2. And in lecture number 2, we also began to explore the trade-offs associated with the use of overhead when we're performing compression. So if we develop clever tricks for compression, adding a little bit of overhead to our compressed bit stream can be helpful. Adding a little bit of extra data to tell the decompressor what clever tricks I'm using can be helpful because maybe it results in me achieving better compression. But on the other hand, when it comes time to actually generate our sequence of zeros and ones, we might discover that no matter how clever we thought our trick was, the amount of overhead we need to generate overwhelms the possible compression advantage, or it waters it down to the extent that my tricks aren't so useful after all, no matter how clever they might be on paper. So that was lecture 2. In lecture 3, we talked about the start-to-finish design of LZW. So a scheme to take a sequence of symbols and produce a different sequence of symbols. And one of the hallmarks of LZW is that the set of possible symbols that comes out is larger than the set of possible symbols that goes in. So if I send in a bunch of 8-bit symbols, I might get a sequence of 9 or 10 or 11 or whatever bit symbols coming out. And the idea is I've created this symbol table and I've defined new symbols that represent common patterns that occur in my data. So if I use only 9 bits, I only get 256 extra symbols, but LZW, at least in theory, is allowed to fill the symbol table for as long as it wants. The symbol table can keep growing as my input sequence wears on. And one of the other characteristics of LZW, something that is common to all of the other schemes in the LZ family, is identifying, macroscopic sequences of symbols that appear over and over again and recycling them. So instead of transmitting BANANA to the decompressor, that's 6 symbols, I could just transmit BAN and then tell the decompressor, hey, instead of giving you the AN, could you just recycle those last 2 symbols, please? And ideally, if I do this a lot, I can end up saving some space because I could turn basically these 2 symbols into 1 symbol if I want to recycle it in the future. And so LZW does that, and we talked in lecture 3 about LZW sort of at a theoretical or symbolic level. We kept the idea of using 9 bits or 10 bits in the back of our heads, but we didn't talk too much about how do we turn LZW symbols into zeros and ones. Okay, so then we got to lecture number 4. In lecture number 4, we talked about, now that we know what LZW is, how do we implement an LZW encoder and decoder that achieves compression? And that would be the ancient Unix compress tool. And we observed that the more bits we can use for our extra symbols, the better, because the more extra symbols we have, the more patterns we have to exploit. On the other hand, if we use too many bits, that introduces so much overhead that we're unlikely to see a compression advantage, especially on short inputs. So one solution would be to use a small number of bits at first, like 9 bits, and then work our way up, 10 bits, 11 bits, and then so on up to, in the case of the Unix compress tool, 16 bits. We also noticed that as time went by, because the symbol table just keeps growing and growing, as time goes by and we go later and later into our input data sequence, the symbols that we created earlier are likely to become irrelevant, because the patterns that we tend to observe in real data have a sort of recency bias, which is that, generally speaking, if you're looking for patterns at this point in your input stream, they are more likely to appear here than they are way back here, because generally speaking, related data gets stored together if you think about real data. So that was lecture number 4, looking at the practical side of implementing LZW. And so that brings us to lecture number 5, which is a lecture that I've mentioned a couple of times is going to be called Basic Techniques. And so by waiting until 5 lectures into the course to receive all of this important information about basic techniques, we have also learned the skill of patience. And so today I want to talk about these basic techniques. But first, let's have some fun with acronyms. So ATM machine. Well, ATM actually stands for automated teller machine. So ATM machine is like saying automated teller machine. But if I were still the type to go to ATMs, which to be honest in 2023 I'm sort of not, and if I were the type to talk to people about going to ATMs, I probably would say I'm going to go to the ATM machine. I might say ATMs, I might pluralize it, but if I talk about a single one, it just sort of feels better to say ATM machine, even though yes, I know the M already stands for machine. LCD display. Well, LCD stands for liquid crystal display. And yet, if I happen to be talking to somebody about my monitor on my computer, which to be honest, I don't really do, I would probably say, I have an LCD display. Even though it would be grammatically correct, understanding this acronym, to say, I have an LCD. It just doesn't feel right. It just feels incomplete. It feels like I'm leaving you hanging if I don't say LCD display. PIN number. Well, PIN number stands for personal identification number. If I'm writing software for one of those ATM machines from a minute ago, I would probably include a prompt that says, enter your PIN number. It just feels better to say PIN number, even though, yes, the N already stands for number. PDF format. Well, PDF stands for portable document format. Okay. So if this were a course where I accepted written assignments, and spoiler alert, it isn't, you're handing in code, then I could say to people, please submit your document in PDF format. I could also say, and it would be grammatically correct, to say, please submit your document in PDF. But it just feels wrong. I want to say PDF format. It just feels like the sentence completes better. It resolves better if I say PDF format. And if you think about how you use acronyms, maybe you do this too. Maybe it just feels right to include this extra word, which, to be clear, is in fact completely redundant. I don't need it because the F already stands for format. I am in fact repeating myself. And then UPC code. Well, UPC stands for Universal Product Code. And to be clear, when we talk about a UPC code or a UPC, that is, for example, the barcode on the back of a box of cereal that you might be buying. Or whatever other groceries you're buying. I'm talking about cereal because I'm recording this at 9 o'clock in the morning. So we could say UPC, please scan the UPC. But I would probably rather say, please scan the UPC code. It just feels better to say it that way. And it turns out there's a name for this. I mentioned in the last lecture that I don't want to go pulling up Wikipedia articles on my videos because sooner or later, if I do that, then soon enough it's 2 o'clock in the morning and I've been reading Wikipedia on video for 12 hours and we're staring at the article for like the Chorleywood bread process or something like that. But you can go take a look at this. Wikipedia is very helpful for having these weird articles about cultural phenomenon, and it has an article about what's called RAS syndrome, RAS syndrome. And of course, RAS stands for Redundant Acronym Syndrome. But if I said Wikipedia has an article about RAS, that doesn't make any sense. It just sounds weird. It feels better to say RAS syndrome. It's another example of one of those cases where the acronym, pronouncing an acronym feels a bit weird, and those of us, and that's all of us, I guess, in the tech business sort of know this. We hear all these acronyms thrown around all day, and they all feel sort of weird to say. So sometimes we add extra padding that we don't need. Sometimes when we speak English, we deliberately add redundancy. That happens in spoken English, that happens in written English. Sometimes it's about making our sentences just feel right, even if it's unnecessary, even if it's redundant. Oh, there's also this one. This is actually a multilingual one. Please RSVP. Well, okay, RSVP translates to basically respond please. So respond please. I'm not going to attempt to pronounce the French words because I don't want people on the internet knowing my terrible French pronunciation. Please RSVP. If I just say RSVP, I don't know, it doesn't sound very polite. And as a Canadian, I suppose it's fine to say please twice in a sentence. That's nice. But this is another example of one of these uses of a redundant acronym. And so we know that universal compression is impossible. We know that even in the best compression scheme, by design, because of the mathematics behind it, in the best compression scheme ever, if it's lossless compression, I can expect that there will be some inputs that get expanded. It says here might even expand. This is trying to be magnanimous and observe that there are schemes where no inputs expand, but that's like the identity function where nothing compresses either. If I get compression, I will get expansion. And so that's even in the best possible scheme. Now, there are things I can do to mitigate the expansion a bit. Because of the mathematics involved, I can try and make it so that when inputs expand, they don't expand by very much, for example. Because of the amount of bandwidth available, if I use more bits than I need, there are more than enough possible input strings of length n-1 if I need something of, or n+1 if I'm trying to expand something of length n. That's something we won't worry about in this lecture. So, of course, that means what we do is we focus on compressing real data. Now, we should be asking ourselves the question, what is real data? Which I assume we've been asking ourselves for the last few lectures. For now, we'll persist with our intuitive definition. We will try and construct a concrete definition of what I mean by random sequences of bits, for example, I think 2 lectures from now. And we understand that if we design a scheme, there will be some inputs that don't compress well or that even expand. And one very common feature of real data, even by an intuitive definition, is redundancy of some sort. The redundancy that we've already seen by talking about LZW, I'm going to call that, I guess, macroscopic redundancy, if I ever need to distinguish. So the idea here is that this subsequence, AN, appears more than once inside the word banana. There are 2 symbols next to each other that where that sequence of 2 symbols has already appeared. So that's a recurring pattern of multiple symbols. It turns out that redundancy can also exist at a symbol level. So, and we'll talk about this in a couple of lectures, but if I take a look at an input sequence where the frequency of particular symbols can differ, so here is an input sequence with 1 letter B, a whole bunch of letter A's, and 3 letter N's. In this case, there is a certain amount of redundancy. You could think of redundancy in terms of the frequency of symbols. Some symbols are more common than others. There are lots of techniques that we can use to exploit that. If I'm encoding symbols in bits, for example, what I could choose to do, and again, we'll have a whole lecture on this later, is I could observe that the common symbols, so A, because they appear so often, if I can find a way of representing A in relatively few bits, I'm going to observe quite a savings. So if I take all of my A's and I encode them in, I don't know, how about 2 bits? So I'll encode them as 0, 1. And then I take all my N's and I encode them in, I don't know, 3 bits, so 0, 0, 1. And then I take my letter B and I encode it in 4 bits. Well, yes, B ends up encoded in more bits than A, but B occurs so infrequently, I mean, I only see 1 B in the whole sequence, that disadvantage isn't that big of a deal if I'm allowed to get this nice advantage of using only 2 bits for A. I could actually prune it down further in this case. I could represent A with only 1 bit, just the bit 1. If you see the bit 1 by itself, that's an A. If you see a 0, 1, that would be an N. And if you see, I don't know, 1, 0, that's a B. So there actually are a few techniques you actually, maybe we won't do that. Maybe we'll use 0, 0, 1 for B. And we'll come back to that in a couple of lectures. This idea that we could use a different number of bits per symbol as a way of fairly valuing a symbol. So the most common symbols have the lowest value, I guess, so by the law of supply and demand, therefore they deserve the lowest number of bits. Whereas the most rare symbols are more expensive, we could think of, and therefore should be represented in more bits. That is also a certain type of redundancy, because there's a certain amount of information that's captured in the frequency of a symbol. We'll talk about that later. So for today, we can think of redundancy as meaning things like this macroscopic redundancy of I see the same subsequence of characters multiple times in my larger input sequence, and I want to exploit the patterns that produces. And redundancy itself is pretty common in real data for lots of reasons. So one reason, I mean, sort of a bizarre one, is occasionally redundancy is added intentionally to data. So occasionally when you store data on disk or in memory, but often on disk for persistent storage, you deliberately add redundancy to it. The slide points out one reason to do that is to ensure durability. There is another reason that's specific to particular domains, which is for increased performance. In some cases, for example, in memory, while running a program, you might keep multiple copies of a piece of data for some reason, so maybe in a caching structure or something, and you might also do that on disk. So database systems occasionally maintain caching structures where even the cache itself is stored on some persistent storage medium. But we'll just think of it as durability being a typical example of why you'd add redundancy intentionally. So if I'm storing something on disk and I want to provide some resilience against errors occurring, I could add error correction bits. And the error correction bits are formally redundant because I don't need them to recover the original data unless the data gets damaged. But if the data gets damaged, the error correction or error recovery bits can be very helpful. That is an example of deliberate redundancy. But for the most part, we don't go out of our way to inflate the size of pieces of data. There are lots of things we do that waste space. That is, there are programs that you write and that I write that use, I don't know, a 32-bit int type, even though the numbers I'm representing will never be more than 10 or something like that. So I don't need 32 bits. In a sense, that's a sort of redundancy, I guess. But for the most part, the redundancy that we worry about in a lecture like this one, or in the LZW lecture, isn't the result of somebody deliberately adding redundancy, or even somebody that's just not paying too much attention and lets redundancy seep in. It's actually a natural function of how you choose to represent data. Consider how, assuming you agree with my earlier point, how, I guess, natural it is to say these things in a redundant way. Say PDF format. You don't need to say PDF format. You can just say PDF. And so that's redundancy. That's redundancy that we didn't go out of our way to add, but it just made sense to add it. It just feels right to put it in there. And the equivalent happens in all kinds of data, not just English text. It happens in other languages, not necessarily with acronyms, but with other language constructs. It also happens in data. Sometimes data contains redundancy that's not deliberate, but it is still there. Patterns that we can exploit. We'll talk later about a certain form of redundancy that's context-based. So if I see the letter Q in a sequence of text, especially if I know it's English text, what is the next character going to be? Is it guaranteed to be the letter U? And the answer is no. I mean, we should assume that there could be input sequences that contain Q followed by something other than U. On the other hand, it is very likely that Q is followed by U. So U occurs, I guess, at a relatively average frequency for English letters. It's probably maybe the 10th most common letter to occur in English text. It's nowhere near as common as, let's say, E or T or A. U is, as I said, maybe 10th most common or so. On the other hand, after the letter Q, U is definitely the most common letter to appear, by far. If I look at all the possible letters to occur after the letter Q in English, U occurs the vast majority of the time. That means that U's popularity or its value changes depending on where you encounter it in a sequence. U doesn't appear that often compared to E, T, or A in English text, but it definitely occurs way more often than E, T, or A when a Q has just occurred. And in a sense, there is a certain form of semantic redundancy behind that observation. But we'll talk about that. That's more of a statistical observation, I guess. We'll talk about that a little bit later. So let's consider instead of worrying too much about patterns in English text, let's consider images, because I think they give us a good case study for the type of redundancy I want to talk about today. So this image contains only black and white pixels. So that means that really, if I wanted to compress this image down to something really small, if I have lots of images of road signs that are all just black or white pixels, and I want to compress them down, what I could do is use 1 bit per pixel. I store the size of the image, and then I just store 1 bit per pixel. 0 if it's white, 1 if it's black, or whatever. On the other hand, if I store this image in a general image format, then I'm probably either storing it in grayscale, so that's usually 8 bits per pixel, or in full color, which is at least 24 bits per pixel these days. It could be more, but for a typical image like computer graphics, I might use like a JPEG image or something. That's probably going to be 24 bits per pixel. So 1 byte each for red, green, and blue. And that means that I'm probably using a lot less bandwidth than I have. I don't need 8 full bits per pixel to represent exactly 2 possibilities. There is also, of course, this other redundancy in the English language. One example that I missed earlier is this English word, the word through. Well, okay, this is the word, this is pronounced through in English. There is another English word that is also pronounced through. So this word, which is, you know, if I have thrown something, then I could say I threw it. This word and this word are different. They are two distinct words, so if I'm going to choose a spelling for them, I have to choose spellings that differentiate this one from this one. On the other hand, this word up here doesn't need to be that long to differentiate it from this one. I could choose a spelling that still makes it different from this word without being as long as it is. That is a form of redundancy, because really the difference, when I read English or any language, what I want to do is decide when I look at each word, what word is that? All I need is enough characters to distinguish one word from another. I am not suggesting that we change the spelling of English words. So one way of using fewer characters for this while still not creating syntactic ambiguity would be to spell it like this, I can't do it. It's awful. But it would solve that problem if I just got rid of these OUGH. And for those of you for whom English is not a first language, I'm sorry about this whole OUGH business. I wish I could tell you how to pronounce OUs and GHs in English in general, but I sort of can't. If I just wanted to differentiate this word from the other version of the word through, then I just need a spelling that differentiates it. I don't need all these extra characters. I don't think we should change the spelling of all English words. I think there are some tweaks we could make to English, to be sure, but I don't think we should change the spelling. I do think that we should observe that this provides us an avenue for compression. There is redundancy even inside of English words, inside of a single English word. And so we can reduce redundancy in general down to a lot of different things, one of which is a theoretical measurement of something called information content. And that includes data implied by context. So you can see I've gotten a bit ahead of my slides here, but the earlier example of the fact that if I see the letter Q, it'll probably be followed by U, well, that means that the letter U actually appearing there isn't very interesting. If I see the letter Q and then it turns out that it's followed by the letter U, that doesn't surprise anybody. That is not a surprise. If I see the letter Q and I find that it's followed by the letter K, that is a bit odd. That's a bit interesting, and it turns out that we actually have a way of formally measuring that level of whether the data is interesting or not is this measurement of information. So the fact that K occurs after Q would be something that is considered to be a higher information thing than if U occurs after Q. We'll talk about information measurements in a different lecture. There are some standard techniques that use information measurements or allow us to use information measurements as a benchmark for achieving good compression. And again, that's not today because we're still apparently talking about basic techniques today. So it turns out measuring information is actually more complicated than we'd like it to be. And so we, in this course, will end up using what I'm going to consider to be a sort of approximation of true information content. It instead measures the information content of a single symbol, as opposed to the information content of an entire huge piece of data. It's possible, given a finite piece of data, to measure its true information content, but it's incredibly labor intensive. It requires a lot of resources. That's something that maybe you could do for a 10-character sequence, but not something you could expect a compression tool to do for a 5-gigabyte sequence. So instead we have to be realistic and use sort of an approximation that captures some of the information content, maybe not every possible dependency. Now, that said, as technology marches on, the amount of computational power available to us now is far greater than it was 10 years ago or 20 years ago or 30 years ago. And so we actually do have the ability to write compression tools that use a lot more information, a lot more data about information content than they did before. But in this course, we'll focus on classical techniques where we rely sort of on this approximation of information content as a way of measuring how much information is in data. And so it can be useful to try and address this redundancy or patterns that occur in data by guessing in advance what types of patterns will occur and working out clever tricks that can reduce the amount of space those patterns take up. And so this lecture it's called Basic Techniques. I'm going to cover two overarching compression tricks, but also a bunch of techniques for eliminating overhead or reducing it. So the basic techniques we're discussing are two compression tricks and a bunch of ideas for reducing how many bits I need to use if I have to introduce overhead. So the first technique I'm going to discuss requires introducing some overhead into our stream, which we of course then want to reduce. And techniques like the ones I'm going to discuss today are often used in pipelined compression schemes. So a compression scheme that combines together a bunch of stages might use techniques like the ones we're going to discuss in this lecture as some of their stages. And in fact, both techniques I'm going to discuss today are parts of the pipeline used by the BZIP scheme. In fact, one of the techniques we're going to discuss today, a technique called run length encoding, one of these techniques is actually used twice inside of the bzip2 pipeline. It's used early in the pipeline and then again later in the pipeline in a separate way, in a distinct way. So back to our image idea. And the images contain the form of redundancy that I want to discuss most today in a more pure form. I don't want to talk about English grammar if I can avoid it, because there's a lot of other confusion that can result from that. So consider this image. This is also a simple sort of line art image. It's not a photograph. It has a very small number of possible colors, like our road sign from earlier. The image is pretty tiny, so 32 by 28 pixels, and it contains only 3 distinct colors. Now, there aren't actually white, black, and pink. The pixels that appear to be white and the pixels that appear to be black aren't fully white or fully black. That's a deliberate stylistic touch to observe that we couldn't count on images actually being fully black or fully white. That might make our lives a bit too easy for this example. Were this a photo, we would probably use a lossy scheme. So because of, as we'll see, the techniques we're going to discuss that tend to produce good results on images don't work so well on photos because they tend to contain a huge number of different colors. And they don't contain what this image contains, which is clusters of pixels, all of which have exactly the same color. Instead, images contain clusters of photographic images contain clusters of pixels that have similar colors, for which there are plenty of clever lossless techniques, but not clusters of pixels with identical colors. We'll talk about techniques for the case where you've got a bunch of pixels of similar colors actually in the next lecture in a different context. Schemes designed for images like this one, so synthetic graphics or stylistic graphics like this one, which I and many people that work with image compression generally sort of group together and call line art. Images that represent line art and not photorealistic stuff, there are a variety of schemes for those images, and images with that characteristic often have a limited number of colors. So in this case, there are only 3 possible colors. Their exact RGB values aren't obvious, but there are only 3 possible colors. So schemes designed for this kind of image, and that includes this venerable scheme from the late 1980s, as well as the PNG scheme, which is a bit more recent, and both of those are lossless schemes for the most part. Schemes like that usually include options to palletize an image. So that is, instead of actually representing each pixel by an RGB triple, so 3 different color values, what I could do instead is I could make a list of all the colors that appear in advance and then just label each color with a number. So this is color number 1. White is color number 1. Here's white, 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 color number 1. Black is color number 2, and pink is color number 3. And you can see if there's only 3 possible colors, and I just label each pixel with a number for which color it is, then I could represent the color of each pixel with 2 bits, assuming that in advance somebody has told me what color 1 is, what color 2 is, and what color 3 is. The basic idea there is what's now called palletization. I've created a color palette, then I've gone and encoded the image using that color palette. And the assumption here is line art images tend to contain very few colors. This scheme uses palletization. It requires it. Once you have an image with a color palette limited to 256 possible colors per image section, so not for the entire image, but for block per sub-block of the image, once you have that, this scheme is a lossless scheme. Of course, encoding an arbitrary image using this scheme here requires palletizing it, which could result in lossy stuff happening, because how do you know that you could use only 256 possible colors? This scheme allows the encoding of full color images. It is a lossless scheme, so PNG is lossless, but PNG does include options to palletize, because in images with a very limited palette, palletization can be a very productive compression technique. And of course, it also factors into allowing things like bit reductions. For simplicity, we're not going to worry about that. We'll talk about palletization and the contours of image encoding later in the course when we talk about lossy encoding. Instead, let's assume that we are representing every individual pixel by a full RGB triple. So every pixel is 3 values, R, G, and B. Each one is between 0 and 255. And together, these 3 values tell you how to mix the color for that particular pixel. If each color is represented in 8 bits, as is the case in the example I just drew up, then that means we're using 24 bits per pixel, which is a lot of space. Here is the top row of the image. So just one row of the image, the top one, so that would be this here. The white pixels actually have RGB value not fully white. It's a little bit off-white, and the black pixels are not actually black. They have a little bit of each color. Okay, so I've got this. I can't just therefore assume this is a black and white row. It is similar to black and white, but not quite. The colors are chosen to be just frustrating enough to not be able to reduce this to some obvious case. If I were to store this entire row using 24 bits per pixel, I now need 768 bits, which is not very good. This is not very much data. Even at a casual level, it doesn't seem like I need 768 bits to represent this. Now, as a point of context, if I begin talking about raw representations of images, we notice that sizes become obscenely massive very quickly. So this image back here is 32 by 28. We used to call that like icon size or postage stamp size. These days, postage stamps, if you can find one, postage stamps have much higher resolution than this. This is an absolutely tiny image. And yet, one row of this image requires 768 bits. If I consider an image of a size that I'm actually likely to see, and I can guarantee you have seen images of this size recently, so a single frame of 1080p video, the dimensions of a 1080p video frame are 1920 by 1080. If I were to store that in a raw representation with 3 bytes, 24 bits per pixel, that means that one frame of video requires 6 megabytes. Or approximately 6 megabytes. 6 megabytes! I should add, you're very well acquainted with 1080p video frames because for the last 30 minutes, you have been watching 1080p video. I record these videos in glorious 1080p. Although as the years go by, 1080p seems less and less glorious, I guess. I don't think we need a lecture recorded in 4K. Every single frame of that video, if we stored it uncompressed, would be 6 megabytes. And the video is recorded at 30 frames per second. So that means that 1 second of this video is 180 megabytes. 180 megabytes per second. Your internet connection is not fast enough for that. And YouTube would have a bit of trouble with its business model. I think it already does. It would have a lot of trouble with its business model if it had to serve video at 180 megabytes per second. And if you're on the UVic Wi-Fi, you're definitely not going to do 180 megabytes per second. So, of course, that means we need compression for video and for images, because storing them raw gives us a ridiculous size for the types of images that we work with these days. So one idea is to observe, well, yeah, there are only 2 colors, but it's hard to assume that every image we work with has only 2 colors. And in fact, this is the first row of a larger image that does not contain just 2 colors, it contains 3 colors. So instead of worrying about trying to think about, oh, there are only a certain number of colors, let's instead look at the characteristics of this row going from left to right. Notice how, it doesn't matter how many colors there are, it does seem as if adjacent pixels are pretty likely to contain the same color, whether that be white or black or whatever. So what I could try doing if I want to represent this with fewer bytes is I could take each run of consecutive pixels and encode that into a pair of, well, this is going to be, I'll call this white, but we understand it's not actually fully white. It's white for 4 pixels. And then the next, I guess, 6 pixels are going to say black for 6 pixels. So I encode the entire row into a bunch of pairs. Each pair consists of a color specification and how many pixels have that color in a row. And the idea is the color specification itself is still going to be 24 bits in size. But I save because I don't have to give the same color specification for every single pixel. I give it once and then I copy it for every other pixel in the run of pixels. So that's one option. I could batch together adjacent pixels of the same color as a way of condensing the amount of space that I need, while still reserving the right to use full RGB values at the beginning of each run. So I could do it like this. I could store the entire thing as a bunch of these pairs, an RGB color and a length. If I were to decide to store all of the RGB values in 8 bits, which is the normal practice for RGB images, at least ones that aren't extremely high definition, then I would use 24 bits for this part. And if I decide that, since I'm using bytes for everything else anyway, I will store my length in 8 bits. So that means that I'm allowed to represent runs of length up to 255 or maybe 256 with a bit of cleverness. That means that each of these runs requires 32 bits. So before, I was using 24 bits for each of these pixels, so that would be 96 bits for this entire run of size 4, and now I'm using only 32. That's pretty good. That's a pretty good improvement. That's an improvement of 3 times. And so now I'm down to 160 bits in total. Because that improvement of a factor of 3 doesn't necessarily apply everywhere. But in general, I'm able to achieve a pretty good reduction. So I reduced this run of size 4 by a factor of 3. And maybe you can agree that the longer the run is, the better of a reduction I see. Because the run takes up exactly 32 bits no matter how long it is, so a longer run gives me an even better savings. So previously I was at 768 bits, and now I'm down to 160. And that's pretty good. That's giving me a compression ratio of, I guess, somewhere in the neighborhood of 5. So that's amazing. Here's the third row. We're going to do the same trick here with the understanding that, yes, white is going to be some actual RGB triple, but to save space on the slide, I'll just call it white, and we'll understand that it translates to some RGB value. If you want to know what RGB value it is, go ahead and use the eyedropper tool on the pixels of this video. And so I can represent this row, so this is the third row of the image, in 288 bits. Remember that previously, if I represented in a raw representation, it would be 768. So with this row, I achieved a pretty good savings. I was down to 160, but you could argue this row is sort of a special case. But with this other row that is, I think, more representative of the types of data you'd see in this image, I get it down to 288, which is a reduction, I don't know, so 768 over 288. That's more or less about 3 times, just under 3 times. That's still really good. That's less than half of the original space using this trick. And this is an example, this idea of representing data that may contain repeating consecutive symbols over and over again. This is an example of something called run length encoding. So I've decided to take the row of pixels and encode it as a bunch of runs of consecutive pixels of the same color. And that is called run length encoding, or for short, RLE. If I were to use the RLE scheme on each row individually, so I take each row like I did a couple of minutes ago, and I encode it using RLE, then I can represent the entire image in 428 bytes. Which is pretty good. I mean, especially given that we've only spent a few minutes coming up with this idea, it's exploiting patterns that occur in this image very regularly. Notice that in the middle of the image, we have these incredibly long runs of pink pixels, so I can expect to achieve a pretty good savings on those. So I get down to 428 bytes versus a raw representation, which would be about 2.6 kilobytes. So I get a compression ratio, if I compare uncompressed to this RLE representation, I get a compression ratio of 6.2, which is pretty good. That we can expect on arbitrary data, even our big 3 schemes don't generally give us compression ratios that are 6 or so. They can, but they don't always do that. So 6 is pretty good. On the other hand, the image has lots of patterns, so maybe this is the low-hanging fruit. If I want to compare the image, instead of comparing the RLE representation to this uncompressed representation, which you could argue is sort of cheating, because I just said a few minutes ago that we don't like to store images uncompressed because they're way too big. So let's compare it to PNG. PNG is a lossless format, and it's able to store this image in 255 bytes. 255 versus 428. And you know, I would say 428 is still a pretty good competitor there. I came up with one technique, tried it in an obvious way, and got it down to 428 bytes, less than double the size of PNG. PNG uses a whole bunch of techniques. In fact, the PNG format is brought to you by the deflate scheme. PNG uses a whole bunch of different techniques, including a certain type of RLE, because it turns out that the deflate scheme, which implements an LZ scheme called LZSS that we'll talk about later, LZSS contains machinery that allows the equivalent of RLE to occur naturally. So there's no need for explicit run length encoding. LZSS sort of provides that for free. So PNG is leveraging RLE and maybe a bunch of other clever techniques that we'll get to when we talk about deflate, and it's getting down to 255 bytes. With just RLE, with my first try at RLE, I got to 428. That's pretty good. If I use this image format, which as it happens actually uses LZW, and that's because this image format was designed in the late 1980s or early 1990s, and therefore in the heyday of LZW, I can get the image down to 151 bytes. And as usual, the reason why this older format is able to achieve better compression is because back when formats like this one were designed, image files were much smaller. So a lot more work was put into optimizing the compression for small images, whereas PNG is able to compress images like this one, but really it's been designed in an era when images were way, way larger. Oh, wait, yeah, that's right. This format stands for Graphics Interchange Format. So there's that redundant acronym problem again. So one question we should ask is, now that we've come up with this clever run length encoding scheme where we use 24 bits for the color and 8 bits for the length, can we devise some input, so an image or a row of an image, that would be expanded? And furthermore, if we know exactly how many bits each run encoding takes, what's the worst compression ratio I could achieve? Those are both things I will leave with you as an exercise, although really I will sort of spoil what the worst case input to RLE is in a couple of slides. So if I take this image, this would be the image of the pair that we're going to have to get to know very well in this course. This is a 500 by 335 image. That is not a big image. That is by modern standards, that is a tiny image. And it requires 614 kilobytes, more or less, if I use my RLE trick from the previous slides. But if I were to store it uncompressed, it only requires about 500K. Now, 500K is still sort of exorbitant for an image of this size compared to what other formats we have available to us. And so I get a compression ratio of 81%, so 0.81 or roughly 0.81 or 0.82, which is bad because it's obviously less than 1 means I've expanded the data. So that's not good. And that shows off the fact, as I mentioned earlier, that the compression techniques that work for line art are a bit different than the ones that work for photographs. Because in this photograph, there are lots of regions of pixels that are very similar, but not identical. They're not regions of solid color. So a technique that leverages regions with consecutive identical pixels can't get very much traction on a photograph. Maybe it does. I guess this area here could be solid black. It could be washing out to solid black, and this could be solid white or solid sort of bright blue or something, fully like the brightness being 0 or the brightness being 100% does mean there could be regions of consecutive identical pixels, but it's very unlikely that there are very many consecutive identical pixels in most areas of this image. If I store the pair in PNG, so the raw representation, the uncompressed representation is about 500K. The RLE representation is 614. So 500K is the number to beat if I want to get better than uncompressed. PNG, which is a lossless format, gets us down to 271K, which is obviously better. I mean, you know, it's an improvement. It's actually a pretty decent improvement too, but it's still not very good if we think about how much space we want to spend on images. We saw in the first, in lecture number 2, that we could get this image down to less than 100K pretty easily without damaging it in any perceivable way. And that's one of the many reasons why we generally use lossy compression for photorealistic images, because they're just too big, and images themselves are stored, if we store them uncompressed, in such a massive representation. So let's talk about RLE, let's stop talking about image data and begin talking about sequences of symbols again. And we can apply run length encoding to anything we want. We can apply it to an arbitrary sequence of bytes or any other kind of symbol, of course. Generally speaking, modern compression schemes, and when I say modern, I mean post-1980s, compression schemes don't just use RLE. And that complicates our discussion of it because that means that some of the disadvantages we're going to see of RLE aren't always disadvantages. And I'll come back to that point in a few slides. So generally speaking, RLE is used as a stage in a pipeline, one of various techniques that are applied. And one reason for that is that RLE is very good at reducing a certain form of redundancy. So if I've got sequences of the same character over and over again, RLE can condense them down quite conveniently into relatively small things. On the other hand, RLE has to add overhead. So in this variant of RLE, what I've decided to do is represent my sequence by a bunch of characters where each character is followed by a repetition count. So how many A's occur? And so in this case, if we let's take a look at the end of the sequence because it's more obvious, there are exactly 4 G characters. When I get to the end of the sequence, I store 1 byte to represent the character G and then 1 byte to represent the number 4 as an unsigned integer in 8 bits. So my RLE sequence will therefore consist of a bunch of byte pairs. Every second byte, starting with the first one, is a character, and the alternating bytes are counts. And this should be an obvious example of overhead. I've added extra data to my stream to represent these counts, because I do hopefully save data when I'm done. On this particular, hand-picked example, I go from 46 characters down to 14 bytes. But maybe you can see the overhead could be costly in some cases. One of the reasons that RLE is used in pipelines is that although RLE introduces overhead that could be costly, often the overhead has very obvious patterns in it. So, for example, a bunch of characters, a bunch of runs of length 1 in a row will produce a bunch of 1 bytes separated with 1 byte between them at a time. And that means that other stages of a compression pipeline might be able to pick these up and reduce this overhead in their own way. So this scheme uses an 8-bit run length after each 8-bit input value. What's nice about using an 8-bit run length is that now, if my run has length up to 255, or maybe even 256, if I'm a little bit clever, I am able to represent it using only this pair of bytes. So if I write the pair A255, where I represent 255 as an 8-bit unsigned integer, then I can expand that out to 255 A characters pretty easily. So using 8 bits for the run length allows very long runs to be stored. And on this input, which is full of runs of reasonably long length, so, runs of length 13, runs of length 14, runs of length 10, and then a couple of runs that are shorter than that, I get some pretty good savings. But on the other hand, there is, as usual, this trade-off where if I add overhead, I'm setting myself up to expand certain inputs. And in this case, what I'm expanding tends to be inputs that have very short runs, because I have to add this extra byte with the run length after every single character. And that doesn't give me a savings unless I have a few runs that are pretty long. So if I have runs that are only of length 1, well, then each individual character ends up being 2 bytes. I'll just write it like with a slash here. So there's B1, and then this is C1. So I get inflation. I actually go from having 3 bytes to having 6 bytes. So there's 3, there's 6. So I take a loss if I have runs of length 1. In the previous example, there were runs of length 1. So F has a run of length 1. And I took a loss. That could have been stored more efficiently as a single byte if I just left it in the input format. However, because I was making a profit elsewhere, I make such a profit on A and B and C that I don't mind taking a loss on the runs of length 1 of E and F. In this input, every character is in a run of length 1. So that means I take a loss on every single character, and so predictably I go from 15 characters to 30 bytes. So I double my input size. So I'm expanding. I'm expanding by a lot. As I said at the beginning, expansion is something you can't generally prevent, but you can mitigate it. You can make it so if it expands, it doesn't expand by a factor of 2, if you're clever. So, okay, as usual, we have a trade-off. Short runs get expanded. If I have a run of length 2, so if I have 2 A's in a row, well, that's going to end up being A/2. So this is 2 bytes for my run of length 2, and this is 2 bytes for my run of length 2. So I actually break even with this representation if my runs have length 2 or more. If I had 3, then I would make a profit, because I used 3 bytes to represent 3 A's in a row, but still only 2 bytes to represent a run of length 3. So in this case, it's only runs of length 1 that are a problem. On the other hand, if all of the runs have length 1, then I'm in quite a bit of trouble. If I use RLE on input data where I can't assume I'm going to have lots of runs of length greater than, let's say, 2, then I have to be very careful how I represent the overhead. So if I use this 8-bit run length, then I have to open myself up to the possibility that I'm going to double my input size if you encode a bunch of runs of length 1. So there is a trade-off I could make here, which is, well, I could just use fewer bits for my run length. That would certainly save me some bits. And so that's one option. It's also worth noting here, as I foreshadowed this earlier, that if I consider this input here, this is an expansion. If my compression scheme is just RLE, then I've just doubled the size of my data. On the other hand, if RLE is part of a pipeline, so I feed the input data into RLE, and then from RLE, I feed it into some other magical technique that's good at eliminating patterns, notice that the data that comes out of RLE is full of patterns. I've got every second byte is the binary value 1. So some other compression scheme that's good at eliminating recurring patterns, and actually we might have already seen one of those, some other compression scheme that's good at eliminating patterns could go to work on this and negate some of this disadvantage. It could take this expanded input and compress it back down again. So keep that in mind. We shouldn't necessarily use every technique we're seeing today as the be-all and end-all of RLE. Depending on the pipeline it's in, there could be reasons you do want to use 8-bit run lengths. So one idea to reduce the overhead, to mitigate that expansion, is just don't use 8-bit run lengths. So if I use an 8-bit run length, and for the sake of clarity in this lecture, I'm going to assume that our 8-bit run lengths are 8-bit unsigned integers. That means that I can represent values from 0 up to 255. Connoisseurs will notice that I will never ever need a run of length 0, so I could actually use 200 runs. I could repurpose this scheme to give me runs of length 256. Well, with some ingenuity. I think you all are ingenious enough to figure out what I mean by this. For the sake of clarity, though, I'm going to treat these as unsigned ints, and therefore the largest run I can represent is a run length encoded as 8 bits, which would be 255. So I get it that yes, we could get a bit longer than that, but maybe for the sake of clarity, we shouldn't. So if I can represent runs of length up to 255 with 8 bits, maybe I observe, hey, the data that I tend to be working with doesn't have runs that are that long. And even if it did, I could encode them as 2 separate runs if I wanted to, and I'll show that off in a minute. So I could use 4 bits per run. And in this particular input, where if I use 4 bits per run, that gives me a range of 0 through 15 for my run lengths. And again, yes, I get it. You never have runs of length 0. If I have a maximum run length of 15, in this input, I never run over that limit. So all of my runs are shorter than 15. So in this case, if I use 4 bits per run length, then each pair takes up 1.5 bytes. So instead of being 16 bits, it's 12 bits. And that's actually a savings across the board. I mean, every run is still representable, and so I actually get a savings on every single run, not just short runs. But notice how here, the runs of length 1 no longer take up 2 bytes, they now take up 1.5. I'm still taking a loss on runs that are of length 1, because a run of length 1 as a single character is 8 bits, but as a run, it's now going to be 12 bits. So fair enough, but I'm taking less of a loss than I was before. Also worth noticing is if I have a run of length 2, that's going to be stored as h followed by the binary representation of the number 2, which is going to be 12 bits. Whereas my run of length 2 in the input would be 16 bits. So now, unlike before, I am making a profit on runs of length 2, but I'm still taking a loss on runs of length 1. So if I look at my worst case input from before, I still get some expansion. If all of my runs have length 1, then I'm adding 4 extra bits per symbol, which means I'm going to get an expansion of about 50%. Well, so really this is going to be 22.5 bytes, but we don't want to talk about 0.5 bytes. So if we're representing things on disk in bytes, it's going to be 23 bytes. So I go from 15 up to 23. Well, hey, that's better than 30, right? I mean, I've mitigated my expansion a bit, but I'm still getting expansion. But maybe no big deal because we're always going to get expansion in some cases. I could just, extrapolate further and say, hey, wait a minute. I was able to achieve a savings in all cases in this input by using 4 bits instead of 8. 8 bits is too much for a run length for inputs like this. So if I use 4 bits, I get a savings. So previously, if I used 8 bits, I go down to 14 bytes on this input. If I use 4 bits, I go down to 11. So I realized a savings even on this input that already was performing pretty well. On the worst case input, I also get a savings. So it sounds like reducing the number of bits is a good idea. So why not just keep reducing the number of bits? Let's use 2 bits instead of 4. So I could do that. If I use 2 bits for a run length instead of 4, then I'm taking way less of a loss for runs of length 1. So there's that run of 1f. Notice how now, instead of being 12 bits, it's 10 bits, because I've reduced the number of bits. On the other hand, as the maximum run length gets shorter and shorter, you eventually end up with large runs not being easily encoded into a single run length pair. So, for example, this is a run of 13A characters, and I have to represent it with a whole bunch of different pairs. So we'll notice it's 1, 2, 3, 4, 5 pairs. So first 3 A's, then 3 more A's, then 3 more A's, then 3 more A's, then 1 more A. So that's the trade-off I have to make. If my run lengths are too small, then a really long run has to be broken up into multiple short runs. However, notice that I still get a savings. I'm still achieving pretty good compression. although the advantage has gone down. When I used 4 bits, I got the whole sequence down to 11 bytes. When I used 2 bits, it's now back up to 24 bytes. But on the other hand, I've sort of moved the complexity around. Now, if I work with runs of length 1, I don't pay as much of a penalty. In exchange, when I work with long runs, I do pay a bit of a penalty because long runs have to be expanded out into multiple pieces, multiple run length pairs. So I'm back to 24 bytes. I think though that actually for this purpose, for inputs of approximately this length or maybe 100 or 200 characters, this is sort of a decent compromise. If I'm going to see runs that are about this length in general, you might observe that although I do need more space than before to represent this run of length 13, I still observe a savings. This still requires, and you can go count yourself, but this still requires fewer bits than representing each character in a raw representation. So I think this is a nice trade-off if I'm deciding to use a fixed number of bits for the run length. And if I look at the overhead in the worst case, now instead of doubling my input size for the worst case input, it goes from 15 up to 19 bytes. That, as far as expansion is concerned, is quite a bit more palatable. Somebody who sees expansion in practice would say, well, that's too bad, but 19 bytes is a bit more manageable than 30, certainly. I'm not doubling my input size. Another option, though, so I could observe that, maybe I'm going to have long runs. Maybe I have an input file that's full of lots of long runs and lots of short runs. I've got runs of length 100. I've got runs of length 1. So I don't want to use only 2 bits per run length. I like having this 8-bit run length because it's good at shrinking really long runs down to almost nothing. So another idea for how to eliminate the overhead is just be a bit selective about which runs I choose to encode. So in the example we just did, every single input character got turned into a run length pair, whether the run was long or whether it was short. Maybe if I'm clever, and in this case, we have to be very clever because I need to make sure the decompressor still knows what I'm doing. Maybe if I'm clever, I can arrange it so that only runs where I make a profit actually get encoded. Or at least I'm less likely to take a loss on obvious cases. When I say obvious cases, I mean runs of length 1. So if I have an input that looks like this, well, if I say, well, I'm going to take a loss on runs of length 1. You know what? If you look at average data, you're probably going to see a lot of runs of length 1. If I look at English text or any other file format, I will probably see a bunch of runs of length 1. So I don't want my scheme to fail miserably on runs of length 1 because runs of length 1 are pretty common. If I could design a scheme that still fails miserably on runs of a certain length, but not length 1, then maybe I've moved the problem to a less noticeable place. And I think that's the idea behind idea number 2 here. So when I encode runs in 8 bits, I'm only going to make a profit on runs of length 3 or greater. If I use 4 bits, I can make a profit on runs of length 2, but if I use 8 bits, I can only make a profit on runs of length 3 or greater. Runs of length 1 result in expansion, which is nasty, as we saw in the previous set of examples. So what I could do is try and split the difference. I could only use RLE to encode runs of a certain minimum length and not emit any overhead at all for very short runs. And so what I'm doing here is I'm trying to prioritize long runs and short runs, and in exchange, I'm willing to sacrifice a bit of efficiency on what I guess we'll call the medium length runs. And so one scheme, I think the best example of a scheme that realizes this idea is one of the variants of RLE used in bzip2. I say one variant because, as I said earlier, bzip2 actually uses 2 different RLE stages. So the way this works is when we first see a character, we just emit it as an ordinary character. When we see a second occurrence of the same character, we emit it as an ordinary character. When we see a third occurrence of the same character, we emit it as an ordinary character, on the grounds that there are probably going to be lots of runs of length 1, 2, or 3. And we don't want to waste space storing extra overhead for runs of that length. But then we adopt a convention that if you ever see a run of length 4, you first print out the 4th character as a regular character. But for both compressor and decompressor, once you have seen 4 of the same character, then I guess it's pretty likely you're going to see a 5th. And that means after you've seen 4 of the same character, then you are required to emit a run length. So then I would say there are 1, 2, 3, 4, 5, 6, 7, 8, 9 more A characters. So after 4 bytes are the same in my compressed symbol stream, then the next byte is guaranteed to be an 8-bit unsigned integer telling you how many more A's occur after that. It could be 0. I could be unlucky and have a run of length exactly 4. But maybe you'd agree that odds are, if you've seen 4 A's, there's a decent chance you'll see a 5th one or a 6th one. So this is selective. It only bothers encoding a run length after you've already seen a run of length 4. It doesn't bother with a run length for runs of length 1 or runs of length 2. And I can show off the example. I can expand it out on the slide. So here I see the first 4 A's, and I just print them as regular characters. Once I see the 5th A, then once I see the 4th A, the next byte has to be a run length. So the 5th byte, whether or not there actually were more A's, after you see 4 of something in a row, the next byte is always going to be a run length. And it's how many more A's after the 4th one. So there are 9 more, because there are 13 in total. So I print the binary value 9. And then there are the B's. So I print the first 4 B's, and there are 10 more B's after that. I print the first 4 C's, and then there are 6 more C's after that. I keep going. And then the next few runs, so here's 3 D's. Well, I print D, I print D, 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 and then I'm done. And then I just go on to E. There weren't 4 D's in a row, so I don't bother with a run length. And you can see already I'm saving some bytes here. I don't bother with a run length for short runs, so I don't run into that pathological case where I have all these runs of length 1 eating up tons and tons of extra bits. Then I print out my 1E, and it's just the letter E, no run length. I print out my 1F, and it's just the letter F, no run length. And then I get to my run of exactly 4 G characters. So there are 4 G's. So I print out the first G, the second G, the third G, and then the 4th G. But now I've tripped over the run length threshold. If I ever see 4 of one character, I am required to emit a run length. And in this case, bad luck, it turns out there are no more G's. There were exactly 4 G's. So my run length is 0. Well, that's too bad. And maybe you can already see what the worst case input's going to be. If I have a run of exactly 4 G's, then I take a loss because I need 5 bytes to represent 4 G characters. Now, consider that if I have a run of 5 of something, so if I have H, 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 well, that has to be condensed down to 4 H's followed by the number 1 to represent the number of extra H's after the 4th one. But that takes 5 bytes. So I haven't taken a loss. If I have a run of length 5, I break even. If I have a run of length 6 or higher, I make a profit. But if I have a run of length 4, then I take a loss. And if you look at the result, yes, I took a loss at the end there, but I'm down to 25 bytes. In the first example of this scheme, I'm already around where I was at the end of the last example. I'm not doing as well as I would do if I used 4 bits in the previous example, but what's stopping me from using 4 bits in this example? The technique can still be used. The idea is I'm using selective run encoding. I'm only encoding a run if it's become reasonably likely that I'm actually going to benefit. So after I've seen 4 characters, then maybe it's time to start thinking about batching it up into a run. But I don't bother with run lengths for short runs, for runs of length 1, 2, or 3. And if I look at this pathological input from before, where we had no runs of length greater than 1, we will observe that it comes out unchanged. I don't get compression, but I no longer get any expansion. So now the expansion is likely to happen on inputs that contain runs of exactly 4 characters only. An input full of 4 character runs would probably perform pretty badly in this case, and you can contemplate to yourself exactly what the expansion would be in the worst case. So here, I'm not getting compression on this pathological input because run length encoding can't do any work when there are no runs of length greater than 1, but on the other hand, I'm going from 15 bytes to 15 bytes. I'm not wasting any space. So that's pretty nice. There's the exercise I just mentioned. See if you can think of an input that's going to be expanded. Okay, that's pretty easy. Rewind the video for 30 seconds. But then see if you can figure out the worst possible compression ratio. The reason I keep asking about the worst possible compression ratio is to sort of turn our minds towards the question of if I design a new scheme, is it possible for the compression ratio to be arbitrarily bad, or is there a certain upper bound or lower bound? Like if we have expansion, which we know we're always liable to have, then maybe we can show that the worst expansion that we see results in a compression ratio of, I don't know, 0.5 or something. It'll never be worse than that. We're never going to do worse than doubling our data. There are schemes you can design where if you're not careful, the compression ratio can become arbitrarily small. I can make it 0.0001. In other words, I can inflate the data as much as I want with a well-chosen input. With careful design, you can always avoid that case. But it's worth considering that here, whether there is a worst possible compression ratio and how do I achieve it. Another idea, if we're talking about how to reduce the overhead of run length encoding, isn't to be selective, although, as I hope you're gathering, you could combine these techniques together. It's not to be selective, it instead is to find a way of encoding our run lengths, I'm going to say, less intrusively. So we already tried using fewer bits, but that wasn't really a fix because the fewer bits we use, the less efficient that we less efficiency we get on long runs. What I want is to still harness some amount of that efficiency. I want to be able to encode long runs efficiently and not have an arbitrary limit like I do if I use, let's say, 2 bits per run. But I also want a way of not seeing 8 bits of overhead if I'm working with runs of length 1. So I'm not going to be selective. I'm going to encode all of my runs of length 1 as runs of length 1, but I want to find a way of encoding the number, the actual run length, in a less intrusive format. Using a fixed 8-bit binary format adds a lot of overhead if I don't need all 8 of those bits. So there are a couple of options here, and basically what the first one comes down to, don't use binary. Don't encode it as a number in base 2. I will still use zeros and ones, I'll still encode it in bits, but I won't encode it in a binary number system. I'll try something else. So what I'm going to try is, and we're going to do this a lot in this course, I'm going to use something called unary. So the idea about, when we say binary, when we talk about binary numbers or binary arithmetic, we're actually talking about doing arithmetic in base 2. Bits, so zeros and ones, don't always have to be used to do base 2 arithmetic. Not every representation of bits is a number in base 2. So when we talk about binary, we're talking about base 2 arithmetic. People, and then you may already know, you can of course do arithmetic in base 3, and we are of course all very familiar with base 10, but the natural question is, can we go lower? Is there such thing as base 1? And this is an argument that is semantic in nature. One could argue, no, there isn't, because if you use base 1, all you can use is the digit 0. What does that mean? There is an attempt at base 1, a sort of odd approximation of what base 1 might mean, is something called unary, which I'm going to say formally, to avoid having arguments with people in the office hours, is not base 1. Unary is sort of a clever trick we come up with that we can use as sort of a stand-in for base 1 arithmetic. Okay, so unary encoding is where we represent a value using a bunch of 1 bits. We can think of it sort of as tally marks. So if I want to represent the number 5, this is in base 10, if I want to represent that in unary, I would just do 5 1 bits. 1, 2, 3, 4, 5, and then a 0 to tell anybody reading when the number ends. So in general, to encode, so how about the number 3? To encode something in unary, we emit n 1 bits and then a 0 bit as a way of terminating the sequence, to say I'm now done representing my number. If I want to represent a bunch of numbers in a row, so 5 and then 3, it's pretty easy. I just put 5 in unary. There it is. Then I put 3 in unary. And because of that 0 bit that terminates it, it's easy to know if I'm reading the bits one by one where one number ends and the next number begins. And you'll observe that unary uses a variable number of bits. The number of bits is just the number, the value of n plus 1. So n 1 bits, 1 0 bit. Unlike in binary, where I have to decide how many bits I'm going to use, because my binary representation is impossible to read unless I know how many bits I'm going to use. So if I use unary encoding, the benefit of that is the number of bits I need is proportional to the magnitude of my number. So small numbers use fewer bits. And so if I now turn to a representation where I'm going to do run length encoding, where I'm going to, the beginning of each run, I'm going to represent as 1 character, there's the letter A, and then the next value will always be a unary value saying how many more A characters to print. So there are 13 A's in total. There's the first one, and there are 12 more, and there's 12 in unary. Now, the actual compression advantage I'm getting here is pretty easy to see because each A sort of becomes a 1 bit. It turns into one of the 1 bits in the unary representation. So as my run grows, the run length is encoded into more and more bits. But on the other hand, I'm still saving a lot of space because in the input, these were encoded as 8 bits. Whereas in the output, each contribution, each element of my sequence becomes a single bit. There it is. I guess that's the last A. So it becomes 1 bit. So I go from 8 bits down to 1, plus a little bit of overhead to represent that 0 bit. So that's all right. I'm still getting an advantage. We can see that I'm going from 46 down to 13. In the previous example, the bzip style selective encoding, I only got to 25. In the example before that, where I used 4 bits with a binary representation, I got down to, I think, 11. Here I'm getting to 13 on my first try. That's pretty good. Notice that on my small runs, like the runs of E's and F's, So there's E followed by a 0. I guess we'll use F as our example. Here's the run of Fs. It is a run of one F. So there's the character F, and then there are no more Fs after that. So I need one extra bit to signal that my run has length 1. So I still need overhead. I'm still inflating runs of length 1, but it's much more streamlined. It's much more subtle. So and as a result, I get less expansion on worst case inputs. And that means that I can, do I have the worst case one? No, I don't have that. If I had the worst case input, maybe you could observe, if I see an input like A, B, C, well, that's going to be A followed by a single 0 bit, B followed by a single 0 bit, C followed by a single 0 bit. So unlike my initial example where I was doubling my input, in this example, I am expanding my input, but only by 1/8. So about 12%, I guess, which isn't great, obviously. I'd rather not have expansion. In the selective bzip case, I didn't have expansion for inputs with runs of length 1. But in this case, that's much better, I think. Having only 1 extra bit as opposed to 8 extra bits definitely is an improvement. And I'm still getting good compression on longer runs. And the run can be as long as I want because there is no limit to how long a unary encoding can be because unary, by definition, is a variable bit length encoding. Now, what I should do next is think, can I refine this further? So if I stare at this, I realize, okay, this is about as efficient as I can expect to get on runs of one character if I'm not going to be selective. If I'm always encoding runs of length 1 with a run length, I can't do much better than 1 extra bit. So as far as the inefficiencies, this is doing as well as it possibly could do on runs of length 1. So where is the overhead high? Well, compared to the 8-bit binary representation or the 4-bit binary representation, I do need more bits for runs that are long. So a run of length 12, if I were using, let's say, 4 bits in a fixed width binary representation, would only need 4 extra bits for the run length. But here it needs 13 extra bits, the 12 1 bits followed by that 1 0. And if the run had length 5,000, then I would need 5,000 extra bits, or 5,000, I would need the initial character and then 5,000 bits to represent the run length, 4,999 1 bits followed by a single 0. So we can see that the unary encoding, I don't want to say that it's that inefficient, but it definitely results in a more bloated encoding than binary for large numbers. That's because unary is inherently inefficient. Unary is a bunch of 1 bits and then a 0 bit. Whereas if I use base 2, I get the benefit of having 2 possible symbols, and that allows me to pack more information into a smaller number of bits, obviously. So is there a compromise that combines the two? What I want, essentially, is the ability to leverage this variable bit width idea that unary gave me, so I don't encode runs of length 1 in a large number of bits, but still harness the power of binary if I do want to encode a large number. And so the trick I'm going to use is I'm going to use binary encodings of my run length, but the width of the binary encoding will be different for every run length. And I'll unpack that over the next couple of slides. So suppose our run length is 13. Well, okay, if I used binary for that, how many bits would I need? I guess I need 4 bits to represent the value 13 in binary. And I'd rather use 4 bits than do unary, because in unary I would need 14 bits, because I would need 13 1 bits and a 0. So in binary, 13 can be represented much more efficiently in 4 bits than it would be in unary. So if I use 4 bits, how do I tell the decompressor how many bits I'm using? I want to use a different number of bits for every run length, so that I still get the benefit of a small number of bits for short runs, and I can use more bits to represent long runs efficiently. Well, what I could do is I could use an encoding that first tells the decompressor how many bits I need. That has to be in unary. So I represent the number 4 in unary, then I give a 4-bit encoding of my run length in binary. And it's weird, you look at this and say, this seems like I'm actually adding more overhead. But as usual with overhead, it's a trade-off. Adding a little bit of overhead in unary can save me a lot of overhead later. If I store the entire thing in unary, so if I store the number 13 in unary, how big is that? That's going to be, I'll try and line it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, then a 0. If I use this trick, I manage to do it in apparently 9 bits. And maybe I can do even better than that. But I can do 9 bits with this trick, even though the trick is complicated. I first have to give the number of bits in unary, then the encoding in binary, but I do get a savings. And I'm willing to trade some extra complexity for actual bit savings. One question then is, can I do better than this? So I've told the decompressor, I'm going to give you a 4-bit number, and then I give it the 4-bit number. But here's an exercise. Suppose we both know that I'm trying to save space. So we know that I want to use as few bits as possible. And I tell you the run length needs 4 bits. My question is there any situation where I would give you a run length beginning in the bit 0? So suppose the run length was the number 6. Would I want to put that in 4 bits? Well, obviously not. Obviously, if I tell you that the run length has to be 4 bits, then clearly the run length has to be a number that needs not 3 bits, but 4. Why would I waste space by telling you it's 4 bits when it actually only needs 3? If it actually needs 4 bits, what I'm really saying is the most significant bit has to be a 1. Because if it were a 0, then I could do it in 3 bits. So this is the binary value 6. I wouldn't need that 4th bit if the most significant bit was 0. So actually, that allows me to save 1 more bit. If you know that when I tell you I need 4 bits, the most significant bit has to be a 1 bit, well then I don't have to give you the most significant bit. You can assume it's always going to be 1. So when I tell you I need 4 bits for my run length, all I give you are the most significant or the least significant 3 bits. I actually don't give you the most significant bit because you and I can both agree it has to be a 1 bit. And that's what this slide is pointing out. So if I know that I need 4 bits, then obviously the most significant bit is 1, so the only bits I have to send you are the remainder of the bits. So I am now able to tell you that my run has length 13 using a total of 8 bits. So actually, I'm back down to the number of bits I started with, except that I'm allowed to represent really short runs in even fewer bits. So what if my run, remember that if I'm storing my run lengths, typically what I do is I store how many extra characters there are. So to store a run of length 2, I would store that as A and then 1, because there's 1 more A after the first one. If I want to use this representation to store the number 1, or to store the number 0 in some cases, I might discover that I actually can do that in a really efficient way. So let's try that. Let's try storing a run of length 2. Okay, I store a run of length 2. First, I give you the character A. Now I need a way of encoding the run length, which is supposed to be the value 1. Well, how many bits do I need to store the value 1? Well, I guess I need 1 bit. So I have to emit the unary value 1, 0. This is unary for, I'm going to say unary for 1. And then I have to give the binary representation of the value I want in 1 bit. But I don't give the most significant bit, so I actually don't store anything else. That's it. I just store A and then 1, 0. I use 2 bits to represent my run length of 1. Suppose I have a run of actual length 1. This was a run of length 2. If I have a run of length 1, then I have to store the number 0, which is, well, how many bits do I need for that? I guess I need 0 bits to represent the number 0. So I could say, well, there's A, and then I give the unary value of 0. That's this. Which is sort of clever, because if I'm giving you a 0-bit number, I of course don't have to provide you any other bits. So now my run of length 1 is stored just as efficiently as it was earlier, if I use the unary example. So if I go back to my example just using unary, I was storing my runs of length 1 using only 1 extra bit. In this clever variable bit representation, I am still storing runs of length 1 using 1 extra bit, and runs of length 2 using 2 extra bits. If I want to store a run of length 3 or more, then I begin actually adding in the binary encoding right afterwards, and that consumes more bits. But the number of bits doesn't go up as quickly as it does with a strictly unary representation because I can leverage the extra information that I can capture in binary numbers. Okay, so if I do that, I end up with this situation. So when I want to store my run of 13 A's, I store the first A, and then this, which corresponds to the number 12. First, I say how many bits I need. I need 4 bits. And then I give the 3 least significant bits. So how would I decode this? Well, this says I need 4 bits. And those bits are going to be 4 bits, and the first one has to be a 1. So I take the remaining 3 bits, and that's 1100, which is 1100 in base 2 is equal to 12. That's how I got that. I first figure out how many bits I need, and then I unpack all of these other bits. The next 3 bits, if I'm using 4 bits in total, the next 3 bits in the bit sequence will be the least significant 3 bits of my number. Okay, so there's my run of 13 A's, and notice how the total number of bits I need for the run length is 8 bits. So I'm back to the same number of bits I was working with at the very beginning. And then for B, same story, only 8 bits are needed for the combination representation. But when I get to my short runs, like my run of only 1E, C, I need only one extra bit. So I don't have that bulky 8-bit value like I did at the beginning. So I realize a savings. And then for this run of 4 Gs, I only need 4 bits to represent the remainder of the run, which again is a pretty good improvement. And as a result, I go from 46 characters down to 12 on my first try using this technique. The number of extra bits you need, we can actually quantify that. If I think of encoding a run of length greater than 0, because why would I encode a run of 0, or why would I want to quantify that? That's a separate thing. If I look at a run of length 0, so that would be 0 extra characters, it requires only 1 bit, just the unary value 0. If I want to quantify the number of bits I need for runs of length greater than 0, I have to do this because I don't want to take the log of 0. The actual number of bits I need is actually log n all squared plus 1. Now, that might just be a matter of interest, a piece of trivia. I like that piece of trivia because in this line of work, it's surprisingly seldom that I get to talk about log n all squared. It shows up occasionally, but not often enough. It's a neat thing to see. It's an exotic sight to see. So here I need log n all squared plus 1 bits. And that plus 1 is basically the end of the unary encoding, that extra 0 at the end. Okay, that's all great, but as usual, before we know that we have compression, you have to show me the bit stream. So what I want to do for the sake of demonstrating how effective these techniques are on real data, keeping in mind that RLE is typically part of a larger pipeline, is I want to do a benchmark on several sets of real data. And those sets are going to be EnglishWords.txt is a list of English words, one per line, with new lines between them. And it's not necessarily every English word because it's a dictionary I sourced from elsewhere, but it's about 38,000 English words, 38,000 common English words. I will also try compressing the Calgary corpus and the Canterbury corpus. So the Calgary corpus is a collection of files. It is 18 files that have been chosen. This is a long time ago in the late 80s. They were chosen as a representative sample of real data one is likely to see. Files of various formats, text, images. I think there's a core dump in there from the result of running a program and it crashing, executable files, things like that. There's also the Canterbury corpus, which is an updated corpus from the late 90s, which contains 11 files that are also sort of real data that was encountered at the time. And if you look at the Canterbury corpus, you can see that there are even file formats that we recognize today, like Excel spreadsheets and things like that. Because the Calgary corpus and the Canterbury corpus are a collection of files, and I want to do a benchmark of compression overall, what I've chosen to do is to take all 18 files and store them in this. So the tar format is an archive format. It doesn't do compression by itself. So if I look at a file that's just .tar, that is not compressed. It's just an archive with a bunch of files jammed together into one thing. That's why normally when you work with tar files, you take the result and compress it somehow, for example, with gzip or bzip or something. So I've taken these Calgary and Canterbury corpuses and I've compressed them into tar archives. Oh, actually, it turns out that tar stands for tape archive. So tar archive is another redundant acronym. It's a rare example of an acronym where 2 letters represent only 1 word in the acronym, but that's neither here nor there. So here's the result of my benchmark. And the schemes down here are variants of the ones that we just discussed. So C implementations of that. One thing I won't talk about in this lecture is that when I implemented these schemes, they occasionally have to add a couple of extra bytes to the beginning or end of the sequence as metadata or overhead to position the decompressor. So one example is we saw at the end, we had some schemes that generated a bit stream with an arbitrary number of bits that wouldn't necessarily match up to a byte boundary. So of course it has to round up by adding padding. Also, in some of those schemes, an extra marker has to be added to the end of the file to tell the decompressor when the input stream is over. And we'll come back to that later in the course, why we have to do something like that. And so just keep that in mind, that there are a couple of little offsets you'll notice in the data that are a result of adding a small number of extra bytes, a constant number. So here are our 3 data sets. Uncompressed, they come out to about 3.2 megabytes for the Calgary corpus, 2.8 for the Canterbury corpus, and about 337 kilobytes for the list of English words. Bzip is able to achieve pretty good compression. Actually, all of our big 3, that would be these 3, are able to achieve pretty decent compression on all the data sets. The Ancient Unix Compress tool, which is LZW, is actually competitive with the big 3 on these. Not incredibly competitive, but it's there. However, the winner in all 3 cases is LZMA. So I've run the LZMA compressor with this command line, and the command line is basically set compression to be the highest, so use more resources if needed, as many as you can to make compression compression work. This is a flag that I think is called like extreme mode or something, but it's another way of adding in extra features to allow better compression decisions to be made. I've done that for all of the compressors, to be fair. So bzip-9 is going to result generally in better compression than bzip-1, and same thing with gzip. And we'll see what these parameters mean later in the course. So LZMA actually wins in all three cases. Now, we shouldn't expect our RLE schemes by themselves to compete against the big three, but it's good to have that context. That in terms of how compressible this data is, getting a ratio of 3 or 5 or so isn't unheard of. So that's the benchmark that we should be using. That's our barometer. Okay, these two schemes, 8-bit fixed RLE and 2-bit fixed RLE. The 8-bit fixed RLE scheme is the very first one we saw, where each character is followed by a run length stored in 8 bits. So I could store a run of up to 255. So I'll represent that by 111111. My 2-bit fixed RLE is where each character is followed by a 2-bit run length. So every character must be followed by a 2-bit run length. Notice that we're not getting very good compression. I would call particular attention to this example here, englishwords.txt, where the size almost doubles. It doesn't quite double, so doubling the size would be 370 by 70 kilobytes, whereas we come out to 657. But the ratio is such that it's almost doubled the input size. And the reason for that is actually quite interesting, which is if we think back to where our 8-bit RLE had problems, well, we notice that we break even on runs of length 2. We get no compression on runs of length 2, we get an expansion on runs of length 1. So this scheme only has a compression advantage if you have runs of length 3 or more, and presumably a lot of them to outweigh the disadvantage of runs of length 1. But I'm looking at a dictionary of English words, and can you think of an English word that contains 3 characters that are the same in a row? Because I can't, and I also checked, and there's none in there. There are English words that have 2 characters that are the same in a row. I can find a few of them on this slide. There are a couple. There are English words that have runs of length 2, but never runs of length 3. So that means that at no point can my 8-bit RLE achieve any actual compression. Never, because the only case where it would achieve compression doesn't even appear in the English words file. In the other 2 corpuses, there are runs of length 3 or greater. The problem is the disadvantage on runs of length 1 outweighs any possible advantage of runs of length 3 or greater. If we look at the 2-bit RLE scheme, we'll notice that compression is a bit better. So we're getting a better ratio with a 2-bit because we're reducing the amount of total overhead. We still can't achieve compression on English words because there are still no runs of length 3 or greater, although we are allowed to, in this case, we can make a profit on runs of length 2, finally. But we still have expansion on runs of length 1, so we can't do very well on englishwords.txt. On Canterbury, we basically break even overall. The compression ratio is actually a little bit less than 1, so it's 2832 versus 2826, but it's pretty close. So we managed to break even. The overhead is basically canceled out by the compression. If I look at my unary schemes, that would be these 2 things. So this unary RLE would be the basic unary RLE scheme we saw, where every character is followed by a run length as a unary value. So I could, if we consider, let's say, 4 A's in a row, well, that would be 1 A followed by 3 more A's. That's the unary RLE scheme. Unary RLE 4 is the unary scheme, but with selective encoding, like in bzip, where we only bother emitting a run length if we've already seen 4 of that character. So here, if there were 7 A's, I first encode the first 4 as regular characters, then the remaining 3 using a unary run length. V-bit RLE, these would be schemes that, the V-bit RLE is the basic variable bit length one that we just saw, so that would be this one here, using this scheme. And V-bit RLE 4 is that same scheme, but with the bzip logic of only encoding a run if we've already seen 4 characters in a row. When we look at these, we're noticing that we're finally achieving actual compression on our Calgary corpus and Canterbury corpus. The Calgary corpus and Canterbury corpus do contain a lot of instances of runs of long lengths, so runs of length 3 or greater. And in schemes that are efficient in how they represent their overhead, this allows the actual compression finally to exceed the overhead. And so we end up with modest compression ratios, but actual compression. 1.13, 1.15, those are respectable, especially since RLE is just one technique. It's a technique that we often combine with others. On EnglishWords.txt, again, because we have all this extra run length overhead and no long runs that allow us to make a profit, we can't really get compression in EnglishWords.txt. It's also worth noticing that actually we get exactly the same size for both the variable bit and unary representation. And that's because when our run lengths are 0 or 1, we use exactly the same bit encoding for both of these two schemes. When I look at my bzip inflected schemes, so using unary or variable bit encodings, but with bzip, I am able to break even on EnglishWords.txt. And when I say break even, notice how I'm actually using 6 more bytes in the compressed representation. Those 6 extra bytes are because I had to add an end of stream marker. So there's a bunch of extra overhead there, but it's a constant amount. Other than that, other than those 6 bytes at the end, every character is just encoded straight up as a regular character. I never encode any run lengths because I never have runs of length 4 or greater. So overall, in all of this, using these RLE schemes, I am able to achieve in many contexts, in practical contexts that aren't English words, I am able to achieve some modest compression. And we'll see later that RLE is very powerful, both for getting rid of obvious runs of the same character in input, cleaning those out, but also applying RLE to the result of some other compression technique can be very powerful. And I hope to prove that in the next example. So our next technique that we're going to talk about, the last one for this lecture, is something called the move to front transform, which is not a compression technique. It is a transformation. So it is a reversible transformation that takes a sequence of n symbols and produces a sequence of n things that are numerical indices, but fundamentally the same size, and even with the same number of bits required. So I won't say compressed data, I'm going to call this transformed data for this lecture. So this is called the move to front algorithm, and it transforms a sequence of symbols, for example text, into a sequence of indices. Now the reason why it's nice, and move to front, by the way, is used by bzip right before one of its run length encoding stages, in fact. The reason the move to front scheme is helpful is because what it produces has certain patterns that can be exploited a lot more easily than the patterns that might exist in the input. So take a moment to appreciate that this particular piece of input contains only one example of a run of consecutive characters, and it's a run of length 2. There's plenty of repetition, so LZW could do various things with this input, as we saw in a previous lecture, but there are no long runs of the same character. So I want to describe the move to front algorithm. The move to front algorithm itself doesn't produce compression, but maybe it gives us something that's easier for us to compress by other means. So to start the process of the move to front transform, we create what the algorithm calls a stack. And as we go through this, maybe you, like me, will begin to wonder why we're saying stack when really it just seems to be an array that we're shuffling things around in. And at one point, it looks more like a queue than a stack. But they say stack, so I'll say stack too. So what we do is we work out what set of symbols we're working with. And then we make what's called a stack containing every symbol in some easy to predefine order. Now you want to make sure it's easy to predefine so that both the compressor and decompressor can start with the same stack. Generally what you would do is have all the symbols appear in numerical order. So we work out all of the symbols that we intend to see and then make this stack with all of the symbols in order. And the order is predefined. So again, numerical order is a good one. In this, and also for the sake of consistency, for some reason in this algorithm, we call this thing a stack. So the question then becomes, what's the bottom of the stack and what's the top? In this example, the top of the stack will always be index 0 and the bottom will always be index 8. Over time, we'll notice we never actually do any push or pop operations, which is one more reason we shouldn't be calling this thing a stack. Over time, the stack will move around, like the contents move to different indices, but the stack never gets smaller or bigger. You might have caught a minute ago when I said, figure out all the symbols that appear in the input that you're going to work with. Doesn't that require reading the whole input in advance? Isn't that cheating? Doesn't that not give us the streaming property that we want? That's true. And that's why in practice, if you want to work out your symbol set, what you do is make an array of size 255. and just assume that every single possible 8-bit symbol appears, and then list all the symbols from left to right in their usual order. Okay, so you could do that. Because I don't want to fit 255 things on a slide, I'm not going to do that here. But keep in mind, you wouldn't scan the input to figure out what symbols it contains. Just assume it contains every possible symbol, every possible 8-bit value. But for our purposes, let's say we're working with this set of 9 possible symbols indexed 0 through 8. Okay, so how does the transformation work? At every step, I go grab a character of my input. So there's the next character. It's A. I figure out what index does that character occur at in my stack as it currently stands. Well, that's going to be index 0. So I output that index. So my output symbol is the symbol numerical value 0. And then I take that symbol and I move it to be at the front of the stack. But notice that in this case, it already was at the front of the stack, so nothing happens. In the next step, we'll see what happens. So I then take my next character, which is a space. I go find it in my stack. It's at index 8. So I output index 8. And then I take the space character and I move it to the front of the stack. Everything after it gets pushed down by 1. And you stare at this and say, that looks more like a queue than a stack. Yup, it's a lot of things. It doesn't seem like it's a stack, but we're going to keep calling it a stack. So I move, at each step, I take the character, I move it to the front of the stack. All right, now I grab the letter L, and so L is at index 7, so I get index 7, and then I move L to the front of the stack. And all the slides have the whole example worked out. You can use it for reference, but I'm going to skip through it pretty quickly here. So I keep walking until I get to the end. There we go. And I've just encoded the letter S, which was at index 4, and so my stack, when I'm done, is now positioned like this. One thing you should observe is that the size of the stack is always equal to the number of possible symbols, which means that I can represent the indices using the same number of bits. If I have 8-bit inputs, then my indices are going to be 8 bits, which means my transformed data will be a sequence of 8-bit indices. And that means that in all circumstances, my transformed data will be exactly the same size as my original input data. It'll be the same number of bytes. So I'm not achieving compression using this technique alone. Okay, so what's the point of doing this? Well, one thing I'll have you observe is that the move to front transform creates a certain bias in the data because generally a frequently occurring character keeps getting moved to the front of the stack. The more often a character occurs, or more generally, the more recently a character occurs, the more likely it is that it's going to be near the front of the stack. And that means when I go to grab it out of the stack, I'm going to get a low index. So observe that because this sequence contains a lot of characters that are relatively common inside the sequence, I see a lot of low indices. In fact, why don't we try counting the number of times I see indices from 0 to 3. So there are 9 possible indices. So the subset 0 to 3 is less than half of the total possibilities. Let's see how many times I see those. So there's a 0, there's 2, there's a 3, there's a 1, there's a 2, there's a 0, there's a 3, there's a 1. And so notice how common those are. And also if I bring 4 into the mix, so that's just over half of the possibilities, I've eliminated almost everything. So 4 is a surprisingly common number in this output, but notice how larger indices tend to be less common, and that's because the more recently a character occurs, the more likely it is close to the top of the stack. And so what's nice about that is that means if, as at the beginning of this lecture, we begin talking, as we're going to do in a couple of lectures, about the value of particular symbols, the move to front transform creates a certain bias where lower numbers become more common. So I could tailor my encoding scheme to use, let's say, fewer bits to represent the number 4 if I wanted to encode this set of symbols using a variable bit representation, or fewer bits for the number 0 or the number 1 or whatever. And in data with recurring patterns especially, common characters are going to stay near the top and have small indices. And so we can use move to front by itself to produce a compression scheme by first computing the move to front transform and then using a variable length encoding to use shorter encodings, fewer bits for low indices and longer encodings for high indices, on the grounds that we believe that generally speaking, lower indices occur more often and therefore will benefit from that shorter encoding. But there's also a really interesting relationship between move to front and run length encoding. Or, well, RLE encoding, which is another one of those redundant acronyms. So RLE, as we have now learned, stands for run length encoding. And yet you're going to hear me in this course say RLE encoding a few times because it just sounds right. So here is that earlier input, which was full of runs of the same character. Notice that when I'm done with my move to front transform, all of the repeated runs of characters, whether it's the A's or the B's, ends up resolving to be a bunch of zeros. So the first A came out to be at index 0 just by accident, because at the beginning of the algorithm, A was at index 0 of the stack. And then I get a bunch of zeros, because I'm reusing the first character over and over again. Then there's the B, and then I get a bunch of zeros as I reuse B over and over again. There's the C, and then I get a bunch of zeros. So every run of the same character turns into a run of zeros if I use a move to front transform. Now, what's really interesting about that is suddenly I can clear away a lot of the other overhead of RLE, because I can realize that if all of my runs turn into runs of zeros, the only runs I need to worry about encoding are runs of zeros. And so I can eliminate overhead associated with runs of other types of characters, because they're not going to appear, or if they appear, it maybe is a coincidence. So if I have data where I want to apply RLE, the move to front transform can sort of distill all of my various runs of characters into runs of zeros, and so I can focus on optimizing how I deal with runs of zeros. So bzip2, which is a very pipelined scheme, uses both RLE and move to front. It uses two different RLE stages. It uses a sort of an early RLE stage to eliminate a bunch of runs of like obvious long runs in the input data, which can condense the data a bit. And then later it uses RLE again after a move to front transform. And the RLE that happens after the move to front transform is a specialized scheme that only worries about runs of zeros. It's got a bunch of clever tricks to encode runs of zeros really efficiently. The stage right before the move to front transform is another transform that we haven't seen yet, that we are going to see later, that is clever because it increases the likelihood of having a run of identical characters, which the move to front transform can then transform into a run of zeros, and then this specialized RLE can pick up and transform into a very efficient representation. And that's one of the reasons bzip2 performs so well, is it combines together a bunch of compression tricks in just the right order that each compression trick can amplify the one that came before it. Now, we'll get to bzip2 much later in the course. There's one other sort of basic technique, fundamental compression technique, that we have to talk about in the meantime, and we're going to talk about that one using all of the next lecture.